Welcome. We're going to look at counting principles, permutations, and combinations today. This first video is going to focus on the empirical and theoretical probability and whether events will or won't occur. And then I'm going to have a second video about the probability of one, and then a second, what we would call mutually exclusive or independent or not independent events. First, empirical probability is actually observed things. So notice this, let's get back to where we should be. This notation is the probability of a certain event happening. And it's simply a fraction or a ratio of the observed occurrences divided by the total number. So let's take an example here with 96 students took an exam for month 8 in particular, and those that earned A's were 33 students, B's 16. This is just another way to see it that's going to help us with some of our analysis. 21 C's, 12 D's, and 14 F's. Not so good for some people, although definitely good for others. Question 1, probability that a random student earned a passing grade. So we would write that as the probability of A, B, or C. So now that's what we need to figure out. Well, A, B, or C are this many here, and there are 70 of them. There are a total of that 96 shown here. So what we have is a fraction of 70 over 96. Of course, fractions always have to be reduced. And now one of the lessons here is that oftentimes we make decimals for the probability answer or percents. So the fraction can be used, or we can use the decimal, or we can use the percent. And if the fraction is used, we would have ended up saying 35 out of 48. So that is not as common. The actual more common answers is the decimal or the percent. And so it just depends on the problem, which type of thing that we use. Second question. So that was question 1. So the second question here was, what's the probability that a student has earned a failing grade? It just so happens that that many is the opposite with the 70. So instead of 70 over 96, this second one, the probability of D or F, is also the probability of not A, B, or C. But we're going to stick to D or F right now. So we would write that as that 26 over 96, but we could also do it as just simply subtracting these. So we could do 1 minus 0.73. Either way, this one would become a decimal of 0.27, and this one is a decimal of 0.27, or 27%. I'm just going to yellow all of them here to show that they are all. These two are the same, of course, and then here's the percent version. That is actual observed occurrences. Something actually happened. In some cases, we can theorize what should happen, though. So here, this one is more thinking of the sense of should. So possible outcomes by calculating. So it's still going to be probability of a certain event. Let's take this example with a die. So on top, we're going to have the possible occurrences, and underneath we'll have the total. So if you throw a die, there are 6 sides to it. That means there are 6 possibilities. In fact, this is one of the few things I can draw decently, so I'm going to actually do it here. Whoops, maybe not completely well enough. Yeah, let's fix that a little bit. Okay, so let's say that that's where there's one of these little pips, and 2, and 1, 2, 3. So that's part of a die. And so now what we'll look at is what happens. Let's make it as a little table. If I roll it, the chance of my getting a 1 is 1 chance out of 6. And that would be the probability here. If I roll it, the chance of getting a 2 is 1 chance out of 6. Or the chance of getting a 3 is 1 out of 6. You get that idea. Each one of the sides I could land on. So the probability, when they ask here, the probability of getting a 1 is simply that, 1 over 6. Equal sign. The probability of getting an even, now, even ones are the 2, the 4, and the 6. So it would be adding these up, or it would be one of those, one of those, one of those. That means we would have 3 over 6, which of course must be written as 1 over 2, or as 0.5. And then the other one is the probability of greater than 1. Well, the probability of greater than 1, I'm going to do this to show that that's what I was trying to go for. Greater than 1 means all of these here. It doesn't include the 1. And that means it's going to be 5 of them. So it's going to be 5 over 6. Okay, so either as fraction or as decimal, we would be, whoops, not that one, cannot do the 3/6. So that's setting it up like as a table and what they should be, and then adding together the ones that are combined. Well, many times when we do things with dice, it's using 2 of them. So dice is the plural of that. So let's look at this table. We have 2 dice. We're throwing one of them and then throwing the other one, or we're throwing up at the same time. Whichever way wouldn't matter, because you're going to get a number on one, and you get a number on the other, and you're going to add them. So if you roll a 1 and a 1, you get a 2. If you roll a 2 and a 1, you get a 3. But if those were the other dice and it was 1 and a 2, you would also get a 3. So this is where there are some of them where there are more possibilities, like there are more 7s than others, and that's our first one. The probability of getting a 7 is using a 6 and a 1, a 5 and a 2, 4 and a 3. You get the idea. It's all of these here. That's the probability of getting it. So 1, 2, 3, 4, 5, 6. So there are 6 of them, and there are 36 possible, but of course we have to make that a reduced fraction. In this case, we'll do 1/6. Now, we could, of course, make that into a decimal, and so I'll just make sure we get that one as 1 divided by 6. That is, and let's talk about rounding for a moment. It's all of these. They're going forever. So you have to put the approximation, and usually 1 or 2 decimal places make sense. So 1.67 or 1.7, rounding that to 2 would not be good. Or, oops, wait a minute, I put the decimal in the wrong place. Hold on a second. I apologize. Let's go back to here. This was actually 1.0. So it's 0.16. So if I round that, I would take 0.17 or 1.67, or I'll make it 0.17, and I would make that either 16.7% or 17%. I would say this is probably the more common, going a decimal place extra, or that one. I mean, it's really like any of those could be acceptable on there. But I'd say the 16.7 is the one that would resound with most people. But the idea is that you are getting the correct fraction to work with, or you can leave it as a fraction for that matter. Now let's look at this next one, the probability of getting a 2. Well, probability of getting a 2 is, there's 1, and only one place. It's only the result of a 1 on each of them, so it's 1 over 36. Well, now that's a really tiny little decimal. If I did make that into a decimal, I'd have 0.0277, and it repeats for the 7. At some point, I need to make it 0.028 or 0.03. If I'd move this and make that a decimal, though, not a decimal, a percent, I would have 2.8%, which even though it's close to 3%, I think adding that extra 0.8 or that 0.8 on is probably a good idea. But I'd accept 3% myself. So I'm going to leave this one, though, as those numbers. Now, let's take a look at this one, greater than 5. So greater than 5, well, let's put this line here all the things here are 5 or less. Greater than 5 are all the other ones. 10. So what that is, all of those that are greater than, there are 26 of them, okay, with red here. The probability greater than 5 is equal to 26 of them over 36 of them, which would be 13 over 18, which would be an approximate 0.72 or 72%. And so that was really just a matter of adding up all the possible ones that were shown that where it was 6 or above. And then the last one here is a 5 or a 6. So notice each one of these a slightly different thing to them. The 2 and the 7 are similar, but the 2 is so uncommon. Wanted to show that. And then it's a greater than, and here is one number or the other number. So all of the 5s are these, and all of the 6s are these. And there's what, 6 and 5 and 4, so there's 9 of them. So there are 9 actual successes or possibilities out of the 36, which is 1 over 4, which is indeed 0.25 or 25%. So those possible answers here. But the idea of it was that you would get that total, 9 numbers total would satisfy the requirement of a 5 or a 6, either one of them. Now let's look at examples involving cards. Now, some people play using card decks often, so they recognize these combinations or these things like suits and numbers and the face cards. If you are not usually using them or not used to them, then you need to be aware of this information here, that there's 52 cards together. There's 4 groupings called spades, hearts, diamonds, and clubs. Oops. Let's get back to where it's supposed to be. And 2 of them are black, those are the spades and the clubs, and 2 of them are red, and I should do red this way then. And those are the hearts and the diamonds. And each suit has this. Sometimes the ace goes at the end as a 1. So just to be aware of that. One of the problems will actually show that over there and there. So let's find the probability of finding an ace. Well, there are 52 cards in there, and there is an ace in each one of the suits. So that means there are 4 of them. Well, 4 over 52 reduces to 1 over 13, and that's an approximate 0.077 or 0.078 would probably, because it goes on forever with these 7s. So I think I'll round it to just the 2 decimal places. So let me go back here and make it the 7. That'll round that one up, and I'll make that 0.8. So that 7. The third number rounds the second one to up to an 8. And of course, then that would be, if we wanted to make that a percent, we'd move the decimal over twice, and we get 8%. So our answers would be either the fraction or one of those decimals or the percent. That would be good too. Now a face card, we're not talking just one, but we're talking these that have faces, actual faces on them. And there's 3 of them for each of the suits. So there's 3 spades, 3 hearts, 3 diamonds, 3 clubs. So we have is 3 and 3 more and 3 more and 3 more. So we actually have a total of 12. So that's 12 out of the 52, which reduces down to 3 over 13, which is an approximate 0.23 or approximately 23%. Okay, let me mark these up. Now, the last one here is a different look, but it's actually almost the same as the second one. 10 and below with the aces as 1. So that means we would be using all of these, but also with the ace there as the 1. So that means there's a total of 10 numbers. Well, wait a minute. There's 10 numbers that are spades and 10 diamonds, 10 hearts, and 10 clubs. So that's actually a total of 40. So the probability of 10 and going down, I guess, 10 to 1 is 40 over that total of 52, which reduces, of course, to what, 2010 over 13, which is approximately 0.77 or approximately 77%. So those are one of the ways that we'll use the cards, a random pick and out of 52 or such, or out of how many types of things that we have. One of the other places where probability comes into play a great deal is talking about a lottery. So in a lottery, the example here has that there are 55 numbers, like 1 to 55. You get to pick 6 of them. If the 6 that you pick are the ones that are pulled out randomly, then you would win a whole lot, because the chance of getting the right 6 is not so common. So what we're going to do here, we're going to look at, is we're going to have 55 numbers, 6 of them taken at a time. Well, there's lots of possibilities. 1, 2, 3, 4, 5, 6 is one. 1, 2, 3, 4, 5, 7. 1, 2, 3, 4, 5, 8. 1, 2, 3, 4, 5, 9. Or 2, 3, 4, 5, 6, 7. 2, 3, 4, 5, 6, 8. 2, 3, 4, 5, 6, 7. I guess not. Oh, I'm getting myself confused. But they're actually a huge number. So there's a couple of ways to do this. The biggest way, this is going to find, we're going to do what's called a combination. Because the order doesn't matter which of the 6 you pick, whether you pick the number 1, it doesn't matter if it's the first or the 6th one you pick, it's still one of that grouping. We use what's called a combination of 55 things taken 6 at a time. And this can be entered into a graphic calculator, and it can also be done by hand. So I'm going to do this one. The formula for a combination is this number, n, factorial, and this one's called r. So we have 55 factorial over n minus r, and that number factorial. Well, that's 55 minus 6. And then the r factorial, which is 6 factorial. So 55 minus 6 is, 49 here. So we're going to work with, right, I'm hoping I've got my own numbers right in my head here. So we have 49, okay, but it's 49 factorial. That takes care of that. Well, we can write factorials, 55, 54, 53, times 52, times 51, times 50. Oh, this is getting tedious, so I'm just going to leave it off at 49. And we have a 49 factorial, and then 6 factorial, 6 times 5 times 4 times 3 times 2, and we don't even need to put the times 1. I will anyway, just for fun. This part, 49, is 49, 48, 47, 46, all the way down to 1. This 49 is also 48, 47, 46. So all of the numbers after 49 plus the 49, they all cancel out. Now, what I'm going to do, which is essentially what our calculator does too, is I'm now going to look and see what things can go into. So, for instance, 5 goes into 55 11 times. 6 goes into 54 9 times. 3, let's see, 2, I guess I can go, 2 goes into 50 25 times. And then, I think the 3 and the 4, 3 goes into, let's see if I can figure, well, actually, this was it. 3 goes into 9 3 times. And then we can do 54 goes into 52 13 times. So we have now, let's see, there's an 11 and there's a 3. And then there's a 53, never got touched, and a 13, and a 51, and a 25. So if you multiply all of those out, you get a really big, huge number. And what it is 28,989,675. Well, the probability that your 6 is one of those, what we would do is the probability of getting the winner is 1 success out of a total number of possible numbers for it, which is that. Okay. So this number then, this is our total possible. and these are our number of successes. So the chance of getting a winning lottery ticket when it's in this order, 55 numbers and pick any 6, and those 6 have to be the 6 winning numbers, is 1 out of 28.9 million, almost 1 out of 29 million. Wow. Okay, that's, for some people, that's a reason to avoid it. You can also write this by the way of saying 1 in or 1 out of 28, and I'll make it 0.9 million as a shortcut writing, or 1 in. Instead of out of, we can say 1 in 28.9 million. Both of those are somewhat common ways of saying it. Well, this fraction is what I would want to get for the answer for it. So that's how you do that with the lottery. This, or one of the things, this is enterable in a calculator. So if you use a TI calculator, and actually even the others, Hewlett-Packard, Casio, I think all of them have the commands, I just don't know where they are. If you're in a TI, the command is math, and then you move the over in the columns to the probability column, and then down below that is this 3, and it'll say NCR. So if you have a newer one of these, you can, the newer calculator, you can press that one or press enter, and it'll let you enter the N and then the R. Some of the calculators make you enter the R first. So like this one, you would do a 55, then you would go to the math button and do all of that. And after you press enter, then you would be able to put the 6. And if you did that, you would get this number that's over here. Okay, so using the calculator can be very useful for some of these. Now, next, let's look at the probability of not getting a result. And that's where it's just going to be like an opposite thing. So this says not 7. We're using 2 die. These are the 7s. It's all of the others. So 2, 3, 5, 6. So all of the others is 30 of them out of 36. And now if we divide it both by 6, we get 5 over 6. Okay, so that is one of the ways here that we can do that, which by the way is the 80 is, well, that's enough in that, 0.833 and 3. So that means I would have called this approximately 0.83 or 83%. Now, the other way that this could be done is to do 1 subtract the probability that you actually do get a 7. Because with this decimal here, okay, that's the probability of not getting a 7. If we did the probability of getting a 7, we would have 1 subtract, and let's see, that was what, 1, 2, 3, 4, 5, 6. So 6 over 36, or 1 divided by 6, and that was this difference of 0.1666, and it goes forever, so it's an approximation. Well, if we did that, we would end up with this number right here. If we did 1 subtract, we would get, and because that's an approximation, I'll still use it, 0.83333, which is approximately 0.83, 83%, yes. So 1 subtract the probability of getting a 7 is the same 83% that we got if we did just not 7. Not 7, or 1 take away the 7s. All right. There. Now, I think I don't want the yellow one, this one here. Okay, that's better. Now let's look down here at using cards and not a face card. Well, we'll go back up here. When we did face cards, we found 23% or 0.23. So I can do 100 minus 23%, or I can do that P of a face card was 0. And I already forgot, let's come back on up, of 23. 0.23. Well, if I want it to be not a face card, I would do 1 minus, and that would be about 0.77, or 77%. I think what that one comes to. Yeah. We can also do that in fractions here, since we know that face cards are 3 out of 13 of them. We can do 1 minus 3 out of 13, which is 13 over 13 minus 3 over 13, which is 10 over 13, which will actually become the same thing here as 0.77 or as 77%. And those are all approximations there. Now, let's look at the other one. So each one of these, I'm like going back to other examples and doing 1 minus it. The probability of a lottery was this 1 over 28,989,675. So if I wanted to get, what's the probability that I won't get that big winner? It would be 1 minus that 1 over 28,989, 28,989,675. Well, that means this one would have to become that same fraction, 28,989,675 over itself, to remain being a 1. Subtract 1 over 28,989,675. Well, that's just subtracting 1 from here. So it's 28,989,674 over 28,989,675, which is approximately 99.9, 0.9999. You have to go 7 places before you get something that's not a 9, which is approximately 99.9% or 99.99%. So I just stopped after 2 decimal places here. You can't really round this up because it's really not actually 100, but it is so close to 100% that it's often accepted as that. Except we know in a case of the lottery, it really is true that some of the time you do actually get you do get one actual winner. But it's just the chance of that's really tiny. Now, using 2 die, let's find the probability that we don't get a multiple of 3. Oh, now that's interesting. That means we don't get a multiple of 3, so we can't use 3s, can't use 6s, can't use 9s, can't use 12s. So let's go back up to that chart and look. Here is this chart here. So we don't want to use 3, 6, 9, 12. And let's start a clean on that. We don't want to use 3s or 6s or 9s or 12s. So we have to think about how many that those are. So we have 5, 6, 7, 8, 9, 10, 11, 12. So there are 12 possible numbers we don't want. Well, since there's 36 of them that it could be, not a multiple of 12. There are 36, and there's 12 we won't use, and that means that there are 24 that we will. Or we can do that as 1 minus 12 over 36. That would be 36 over 36 minus 12 over 36. And we are right back there with the 12 over the 36, which of course reduces to 2 over 3. So you can do 2 out of 3 chances. Or we can make that a decimal, but it's an approximation, 0.66 forever. I'll round that to 66 or 67, and that gives me 77%, or 66.7%. Okay. Now, we'll close up. So there's a lot that's in here so far. So I've done essentially through 3 of the pages of the notes here. And I will have a second video to continue this with mutually exclusive or independent events. But right now, this gives us a good start to look at. If I bring it back up here, up to this top. So empirical and theoretical probability using a table or chart of some type. And that's where we did this with rolling the die. And then it's analyzing using cards. Again, all of these are actually theoretical. This is what it should be. If you pulled out a card 52 times, 4 times it should be aces. It isn't always, but if you did it 1,000,000 times, you'd probably get that. That would be the average of them. And then face card doing the same thing here, and then doing it with a lottery, and then doing it where it was the opposite, not getting the result. So think of that as this with this 1 minus on it. Okay, thank you for watching. I hope that helps you, and please also look at the follow-on second video for this section.